Evita is on. Okay, the mic is on and I'm here. Good morning, everybody. Welcome to live lectures of celestial navigation. Matthew, good morning. Let's see, is John here as well? Let me know if you can hear me. Let's move the light away. Let's get this baby a little higher. Okay, now we're cooking. Stream is on, lights is on. I have my pencils. If you can hear me, just let me know in the comments so I know the mic is working. I have all the equipment here. Today we have Celestial Navigation live lectures part 1. We're going to talk about celestial sphere. Okay, perfect. Now, Matthew, I'm going to ask you to listen carefully what's going to happen right now in 3, 2, 1. Okay, can you hear what is happening right now? I mean, I cannot hear it, but you can hear it, I presume. And you're supposed to have right now, why it's not picking up? You're supposed to have right now an echo, because right now I have my 2 microphones on. So if you hear this by accident, if there is some change in audio, that means by accident I activated my 2 microphones. One is on the one end of the studio and the other one is on the other end of the studio. So in case that happens, just let me know and I will turn off the second one. So right now I'm turning off the second one. The second mic is not picking up. Let's see why. Properties. Puerto Rico. Let's see. Settings. Audio. Mic. Everything is on. Okay. Video, audio. Okay. Okay. If from moment to moment you lose me, just that means I stepped away a little bit far from the microphone, but I will return shortly. But you should be able to hear me even if I'm like here. This is around 2 meters away from the mic, so just the level of the sound is going to be slightly different. Like I'm back right now and then I step away. But I believe you can still hear me. I can see the spikes of the microphone going up, so it's just the difference of the volume. Okay. Why is camera not picking up? Okay. Let's switch to the camera. Yeah, John's supposed to be here, but let's see, maybe he sent a mail. Okay, so John can hear me. And I already told you, John, that you cannot, I cannot hear you, but I can see your comments. Now, John, can you write, okay, because I guess you still didn't manage to fix the YouTube account. Can you send me an email, please, that you can read the Matthew's comments? Can you see Matthew's comments on the side, on the right side of the screen when you are on YouTube? Can you see the Matthew's comments? If you can see Matthew's comments, then it's okay. And you can also comment. Okay, just I will have my notification on for my email, so you can, if you have questions, John, you can send it on my email and I will check it. But it would be best if you can just log on to YouTube and write comments just the same way Matthew is doing. So John is here, Matthew, but he can only see us. He doesn't have a YouTube account, so he cannot comment. So basically we have everything ready to go. John has confirmed that he can hear me. So we will start soon with the lecture. Let's see. I do not understand why the light is why it's so dark. It looks so dark when I'm looking. Let me just check. Okay, I have a message from John. Okay, so John can see Matthew's comments. Okay, so John, you understand that if you had a YouTube account, you could also comment just the same Matthew is doing. So, but you can send, I just seen your email, so you can send me a message in email if that is how you want to communicate during the live lecture. It's not an issue. So I have John, I have Matthew, I have everybody here. Welcome one more time. My name is Marina Matic. I'm lead instructor when it comes to everything maritime, and today and this entire week I'm going to be guiding you through celestial navigation's basics of celestial navigation. This is a live recording. After a live recording is finished, it will be available on my YouTube channel, so you can review it anytime you want. That is one of the reasons I prefer to do live lecture, because I get to keep the videos for future students. If something is unclear, additionally, after the lecture is over, you can write me an email or send me a message, and I will go through that tomorrow or the next day, or I will prepare a special video just for that, for the specific issues that you have. And that's basically it. Also, I would like to note that this is my own channel. This is my own, not private, but business channel. But for me, it's not connected to any training center except me, my own. So I'm in charge, and everything that happens here is my own responsibility. And of course, I release myself from all the responsibilities that you might have from listening to me during this week. You know, the official disclaimer is somewhere there in the description, so we are safe when it comes to that. Okay, so John is here, Matthew is here, the stream is on. I just want to see, can I change the light, because I'm not satisfied with the light. Let's see. This looks kind of dark to me. Let's see, can I make it a little more brighter? Configure video. So let's camera control. What is going to happen now? Nothing. Let's brightness. Okay, brightness. Okay, this is a little bit better. Okay. Okay, it's not substantially better, but it is slightly lighter, so it's good. Okay. What do you mean, Matthew? You were not told about this. This is free of charge. I'm not being paid for this. This is just me and my love towards celestial navigation, and I want to help you. So I'm not being paid for this. This is not funded by anybody. I mean, I can do something else at this moment, or I can be teaching you celestial navigation. So this is not, this is because I will be your instructor next week, and basically I'm doing this to help myself, to make sure that next week when you come on the official course that is being paid to me by Adria Libar, that you are ready. So this is just my own free will. Okay. I see your point, Matthew. I see your point. So Matthew, this is not official course. That is why there was no announcement. This is just something I decided to offer. And I asked Katrina and I asked the CEO of Adria Liber, are they okay with that? Are they okay with me offering to you or to anybody out there that is connected to Adria Liber, not me, to provide you with lectures live? So at the moment, so that's what I'm telling you, Matthew. This is my own free will. This is me seeing that from the last group and from the groups before, everybody told me that they need more time. They need, the moment they come on the course Monday, by the Tuesday, they realize, okay, we needed 2 weeks to prepare for this. It's we cannot follow the lecture because we do not understand some basics, and plus every course when it comes to Yachtmaster is build up. So for this course you need to know everything from the previous course, and for the following course you need to know everything from this course. And people have tendency to study only for the exam. I'm not talking about you, I'm not talking about people, I'm just talking about how unfortunately some people treat courses like, okay, this is a course A, and once I'm finished I'm just going to forget everything I learned because I will never need this after the exam is over. And that is wrong wrong position to take towards these lectures. The point here is that everything that you learn here, you will need this tomorrow for the following course, all the way up to Master Unlimited. And even tomorrow, if you want to become Master of Merchant Ship, you will still have to go through this all over again. So there is no moment in your future that you will be free from this. So what you learn today, you will have some exam in the future or a refreshing course that you will need to have this knowledge back and usable knowledge. So the reason why I offer to do this is to make sure that the next week you are actually ready for the course. Now, if you want to leave, if you want to leave, there's no issue. I will make the video and you can watch them in the afternoon. You can watch the video later at night. You can watch them tomorrow. You can watch them Saturday, Sunday when you are free before the course. Today and in this entire week, I have scheduled for Celestial Navigation on English language. It will be from 10 and until everybody is tired of me, or because I'm never going to be tired of Celestial Navigation. I absolutely adore Celestial Navigation. But if you cannot be here right now, if you have to leave, if you have to work, if you cannot follow the lecture right now, you're free to leave. I have a couple of candidates here who are from Croatia, and they are also willing to listen to this course, and they have no problem listening to it on English. So Ivana, ako si tu, napiši slobodno u komentarima tako da znam. So another Ivan is here. Ivan should be here, but he's a professional, so he knows. He also has his own tutoring done by me, so he knows that you two, so Matthew and John, you are in charge. You are the first candidates, that because I am officially doing this for you, but you are in charge. Your questions will be answered first. That is the role of my live tutoring for unique candidates. But if you have to leave, you are free to leave. You don't have to stay here. I have other candidates that's going to participate here, so it's not an issue. You can leave. You can ask me if something is unclear in the video after you leave and you watch it in the afternoon. You can write down the comments, or you can send me an email, Marina, at timestamp 26:32 seconds in the video you said something about precession that is not clear to me. Can you provide me more information or something like that? And as you can see now, Matthew, Ivan is here. Ivan is one of my candidates. He's a future officer and master to be, and he is also with me. So Matthew, if you leave, I have Ivan. I always have a backup candidate to torture for a bit Celestial Navigation. Okay, so if everybody is clear on what's happening here, I would like to start with the actual celestial navigation. If there is no more question about what is happening here and why, let's start with the lecture. Okay, Matthew, if you're okay. Ivan is always okay. Thank you, Ivan, for coming, and thank you, Ivan, for confirming you are there. And let's start with the lecture. Yeah. No. Thank you, Red Dragon, for explaining. Matthew, the trick here is Matthew is part of the bigger, course program for future Yachtmasters under STCV, and he is right. This lecture done by me live was not announced officially because I decided, after I've noticed that preliminary exams are becoming impossible for them to fill up without external help, I decided to be that external help. So no, Red Dragon, leave Matthew alone. Matthew has been calculating this all by himself for past 2 months, so he's a good boy. Okay, so let's start with this. You all know what this is. Let me switch so I can see myself. Okay, so this is Earth, made in China, but this is Earth. And if we want to pinpoint a position here of an object, doesn't have to be on the sea, it can be on land, anywhere. If you want to say, okay, this is where I am, and you want to share your position with somebody, what you do is you tell him how far you are from Greenwich and how far you are from the equator. So those two are the coordinates of something that is somewhere on the surface of the Earth, either on land or on the sea. So you tell him your latitude, that is how far you are from the equator, and you give him your longitude, that is how far you are from the Greenwich or prime meridian, east or west or north or south. So that is how you pinpoint your position somewhere on Earth. Now, when you are looking at the sky from, let's say, this position, when you're looking at the sky, you see some objects on the sky. For example, if it's daytime, you see sun. If it's nighttime, you see stars, and you see moon, and you see maybe occasionally you can also see some planets. Now, what we do in celestial navigation is, the first thing is that we imagine there is this invisible glass ball or sphere surrounding the Earth. So imagine there's a glass ball surrounding the sphere around here, and now we have a surface. That glass ball has a surface, so we have inside surface and the outside surface of that glass ball that is surrounding the Earth. Now, if we just copy what we have on Earth on the inner surface of that sphere, so on the inner surface of that sphere that is surrounding the Earth, we copy what we have on Earth. And on Earth we have meridians and we have parallels. So this is what we have on Earth. So let's say I'm here. If this is the equator and this is Greenwich, this would be my position. This would be my coordinates from the equator and from Greenwich meridian. That is how I would say my position is, the location of my position is. Now, this is the inside surface of the glass. On the outside surface of this same glass, same sphere surrounding the Earth, we draw what we see. So, for example, at nighttime we see stars. We see at daytime we see sun. We can also see moon. We can also see planets. And now what we have here, if I face this towards the light, what you actually see is that if this is a picture on a certain date, so month, day, month, year, and then hour, minutes, seconds. So this is a picture of the sky at this moment. So this is a picture of the sky at this moment. When I'm looking at the sky, I can see that it's not an actual value, but it is possible to say, for example, for this star, so I'm picking this star here, this star at this moment has this distance from Greenwich and has this distance from the equator in this moment of time. So in this moment of time, this star that I see on the sky has a unique distance from Greenwich and unique distance from the equator. So no matter where I am, no matter what's my position, these two values are fixed for this star. So no matter where I am, at this day, at this month, at this year, and this hour, this minute, this second, this is the position of this star. This is how far it is from the equator, and this is how far it is from the Greenwich meridian. But this is, how to say, imaginary value on celestial sphere. So that imaginary glass ball I told you is actually celestial sphere, and it is always drawn. So when we are drawing celestial sphere, we do that for a specific moment in time, so not for a duration of time. It's not a video, it's a photo. So this is a photo of what I had on this day, month, year, hour, minute, second. Now this distance from the equator can be calculated without my position, because it doesn't depend on my position. Distance from the equator for a certain object on the sky, so this star, this planet, this sun, it has no influence. It's not influenced by my position. So this doesn't depend on me, and it can be calculated in advance. So for example, if we want to calculate where this star is going to be on any other day, any other minute or second, we can do that, because that value is not depending on our position. We just use 0 and 0. We use equator and we use Greenwich meridian. Now, in celestial navigation, this distance from equator to an object on the sky is called declination. And it can be north or south. So any object on the sky can be above the equator, so on the north side of the equator, and it can be on the south side of the equator. And this distance, so distance from Greenwich, is measured in this direction, because that is how Earth rotates. So Earth rotates like this, and then all the objects are moving in this direction. So we are counting the angle in this direction. So the Greenwich is moving like this, and the objects are moving like this in this direction. So this is a starting point. So when the object crosses the Greenwich, that is 0, and then we have 10 degrees, 30 degrees, 20 degrees in that direction, all the way back to the Greenwich, so 360 degrees. And this is called hour angle. If it's measured from Greenwich, it's also called Greenwich hour angle. So it is hour angle. The reason why it's called hour angle is because it is connected with time. It has connection with time, because it takes Earth 1 hour to make 15 degrees rotation. So that means 1 hour is equal to 15 degrees. So this is angle and this is hour. So Greenwich hour angle, the value of it can be expressed either in time or in degrees. So if I say I'm 1 hour away from Greenwich, 1 hour away from Greenwich, that means I'm 15 degrees away from Greenwich. If I say I'm minus 1 hour from Greenwich, that means I'm west from Greenwich. And if I say I'm plus 1 hour from Greenwich, that means I'm 15 degrees east from Greenwich, because east is plus and west is minus. So, of course, the degrees is what we are looking for. Degrees is what we are missing. Degrees is what we need. So we need our longitude and our position in degrees. But what we need to have, and the way we calculate this, is time. So one of the first things that happened in navigation, not just celestial navigation, but in navigation in general, was that they had a clock here in Greenwich, and then they placed a clock on all the ships traveling around the world. And now, using radio or any other means of connection, they compare the clock in Greenwich observation station and the clock on the ship. And whatever time they get, so if this is 1 hour difference between ship and Greenwich, they multiply that number with 15 to get longitude. So for example, if I get that my ship time, so 2 clocks, are 2.5 hours apart. So 2.5 hours apart. That means 2.5 times 15 is how much? Shall we use the calculator for that? Yes. Why be smart when we can use calculator? So 2.5 times 15 is 37.5. So 37.5 degrees. Now, if it's plus, then it's east. If it's minus, it would be west. And that is how I will get my longitude. Now, what is the base of celestial navigation? So this is how we need. So in celestial navigation, we are using three devices. We are using chronometer. So it's a precise clock that will give us this. It will give us time, and time will give us longitude. And we are using compass to measure the angle where we are seeing an object, any object on the sky, or in terrestrial navigation, lighthouse, or an island, or land in general. And the third piece of equipment that we are using is sextant. So sextant is a device that is used to measure angles. Now the angle that we are measuring is the height of the object above our horizon. The reason why we are measuring this angle is this number is unique. So let's focus on this star here. The person is here. The inclination and Greenwich hour angle of this star is unique, but the height for me on this position is this. For this person, the height from his horizon is smaller, and for this person, he probably cannot see it because it's on the other side of the hemisphere, so he cannot see this star at all. It is not part of his visible horizon, so he cannot see this star. He needs to use this planet or whatever is available. So this value, the height of the object, is depending on your position. But also, this can be pre-calculated. So let's say, just imagine I'm here, or I'm not here. I actually placed a security camera here on this position, or maybe even closer on this position. Now, security camera can take picture of this star 365 days in a year, 24 hours, and measure, this star is now here, now here, now here, now here, now here, now here. And all of that data, when it's collected, it is actually presented in this book that I'm going to talk about later, in Nautical Almanac. So all the values, distance from Greenwich and distance from the equator, is written here in this book. And this can be calculated in advance. So the core of celestial navigation is that you are here. This is your true position. So this is your true position. And you have no idea where you are. This is your true position, but you don't know. This is unknown. What you actually do is, from this position where you are, you measure with sextant the height of this object. And this height is true height for you on this position. No other person anywhere on the planet can measure that star on that height and that bearing. It's not possible. So if I have a person that is on same position as me, but on top of me, like 10 meters above me, on the deck above me, he will have different height. And if I have one person sideways, they will have same height. They will measure the same height of the object, but the bearing would be different. So for me, on this position, on this level from the sea horizon, there is only one height and one bearing possible for this object. No other person anywhere around me can have those two values the same. Now, once I measure these two values, the height and bearing, I put them aside. Because I cannot do anything with those two numbers because I don't know where I am. And what I do is I just take literally globe, or I can take chart or whatever, and I just pinpoint any position I want. I say, this is where I am. This is my position. And now that I know this position, now I know the coordinates of this position, I calculate the height and the bearing if I was here. So what would be height calculated if I was actually here? And from sextant here, I have height true. Difference between these two values is my error between my true position and my assumed position. And that's the base of celestial navigation. Celestial navigation is you are here observing a sun on 50 degrees. And then you say, I'm here. And the celestial navigation tells you, yes, this is very good that you are thinking that you are here, but unfortunately, the only possible location that sun can be seen on 50 is if you are here, somewhere on the circle. Because if you are observing just one object, you cannot get your position directly. It's same like lighthouse. If you have just one lighthouse on the island, you only get one line. So what we need another lighthouse. And where they intersect, we get our position. So the same thing happens in celestial navigation. We need to observe one more star, so we get one circle from where that star can be visible on that height that we measured. We get another circle and from another star, and when those two circles intersect, that is our true position. Or basically, what celestial navigation is saying, this is a circle where star A can be seen, and this is a circle where star B can be seen. And this position here is the only possible position ever on anywhere on Earth where those two stars can be seen on that height and that height. So that basically means this is your true position. That is your true position. And the way you get errors, how can this position be wrong, is if you actually read the height wrong, so you are using the devices wrong, you didn't measure the angles wrong, you didn't calculate the time correctly and stuff like that. But if you are good with calculating, if you are good with measuring, if you are good with using compass, this position should be as accurate as GPS. There is no reason for this position to be wrong if you are doing the reading from the devices correctly. And one of the devices I mentioned during our last lecture was actually this one. I didn't know how to describe this to you, Matthew, but I hope now you know what this is. So this is what we did back in school when I was in school, in high school. Basically what the instructor would do is he would turn this like this, he would make some number, and then he would point this at us and say, okay, read me the centimeters, millimeters, and micromillimeters from this device. And that is what gave me opportunity to, for example, if the value is here, I can read this precisely. But for example, if you have measuring scale like this, 1, 2, 3, and then the line is here that you need to read, and if you say this is 2, of course the number that you're going to get is going to be wrong, because this is not 2, this is 1.7, 1.8. So that is how you read from devices. So celestial navigation is very precise, but it depends on human ability to read the actual value from the device. So far, how many of you did I lose up to this point? Is it clear what celestial navigation is? So, Ivan, give me a proof of life, you know, like on a bridge you have now dead man alert. So give me a proof of life. Matthew, give me a proof of life. Red Dragon, if you are still here, give me a proof of life that you are still here, that you are still with me, that you can follow me. And if the answer is yes, we are actually going to start drawing the celestial sphere. Okay, so I'm going to show you PDF file. So this is the first page of the preliminary exam that you must fill if you are coming on STCV Yacht Master course. So the task number 1 is name the elements of the celestial sphere and draw the sphere. And that is what we're going to do right now. We're going to draw the sphere and we're going to name all the elements of the sphere. So go back to camera. Let's move this aside. Let's get me a bigger paper. Now I'm going to draw this with pencil, and then I'm going to mark it over with marker so you can see it. You can follow me if you have that option and setting in front of you. If you don't have that setting in front of you, you can watch the video later and follow the numbers that I'm going to use here. For Croatian students, you already have this on my web page. It's under Celestial Navigation tutorial, but it is one of the older videos, so practically this would be me recording it again. Let me just find it so I can match the numbers from that video. Celestial sphere, okay. Let's mute this. And let's get the numbers. Okay. Let's write it down. So what I'm going to do here is I am going to, don't worry, I'm still here. I just moved away from the microphone. I'm going to construct a celestial sphere for a person that believes is at latitude of 14 degrees north. The height of the object he observed with sextant is 42 degrees, and the bearing from compass, so azimuth true, is 115 degrees. So that is the data we have. That is the data we're going to use for, let me get this out, live stream. So latitude 14 degrees north, height of sextant is measured with sextant of the object is 42 degrees. That is what we measured. That is the angle from our horizon. And azimuth true is what we read from our compass. So we took our compass bearing, we corrected that for variation deviation. That is 115. And now we need to draw a sphere. So let me get pencil. As I said, you will not be able to see anything right now, but I will, once I draw with pencil, I will mark it with a marker so it's more visible to you. And I'm going to also read you the numbers so you can follow me as well. So let's do it. Let's do 7. I believe is the 7 going to be too big. Let's do 6 centimeters. So 6 centimeters. I forgot to mark the center. Come on, center. So the first step is you need to draw a cross, and this cross is not important. The cross is just a guiding line for you. So 6 here and 6 here. And take compass and draw a circle. And as I presumed, you cannot see anything, so I'm going to just make it more visible. Okay. I hope this is now more visible to you. Okay. Now, the horizon is going to be, and because I told you I want you to be able to follow this, I'm just going to, so what I'm drawing here is, this is Earth in the center. I'm drawing celestial sphere. So this is, I'm drawing the surface of the imaginary ball that is surrounding the Earth. So that means, observer, you are actually here. This is where you are. You are in the center. And then you are standing on Earth like this, and now I'm drawing what you can see. I'm drawing this celestial sphere. I'm drawing this picture. This is what I'm drawing, but much nicer. So the first thing I need to draw is I need to draw my horizon. I need to draw my horizon, and that means this is me. I'm looking like in this direction, so my eyes are facing here, and my horizon is here. Now the way we draw a horizon is, let's make it so the diameter is 6. I'm going to make a dot here at 7.5. 7.5. Same thing on the bottom. And let's say, so I'm putting my divider here, here, and then I draw a line, full line. So full line goes here, Because why full line? Because this is, you need to now have 3D perspective. This is the side of the sphere I can actually see. If I turn my back, I can see the other side as well, but I'm only focusing on 180 degrees. So everything that I can see from my left shoulder up to my right shoulder, if I turn my head sideways, is 180 degrees. So this is the part I can see when I'm facing one direction, and this is the part I cannot see. It is still part of my visible horizon, but it is on the back side from me. And because this is a horizon, usually it is represented with blue color. So blue, 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 blue. So everything that is here is not visible. So everything that is under my horizon is not visible to me. Everything that is above horizon is visible, but only 180 degrees because I don't have eyes on the back of my head. So I just draw my horizon, and everything above that is what I can see. Now, there are 2 points on this sphere that I can automatically get here. I have Z and N. This is zenith and this is nadir. Zenith is the point that is directly above my head. So directly above my head, and 0 is the level of my horizon. So the angle between horizon and zenith is actually 90 degrees. And when I'm observing an object, so for example, let's say I have a star here. I'm not going to look at it 0, 100 degrees. I'm not going to tilt my head backwards and stretch my neck on the other side. So what I'm going to do is I'm going to face this way and measure it from here. So it's going to be 80 degrees. So every object has a height from horizon to zenith, and the value can be 0 to 90. So I have 30 degrees, 40 degrees, 50 degrees, 80 degrees, 90 degrees, and then I have on the other side, it changed bearing on this side, and this circle here is the level of horizon, and this is actually my azimuth level. This is where I measure azimuth of this object. Okay? Let's see. Now, if this is clear, the next step that we need to do is, so we have zenith, that's the point above us. We need to determine the sides, and with the most important sides that we need to determine right now is north and south. So that's the first thing that we draw after we have our horizon. We need to pinpoint where is north and where is south. Now, how do I explain this? You are standing on Earth like this, this is you, and you have the surface of horizon. So somewhere on this level is actual north. So if I'm here, the north is in this direction, south is in this direction, east is in this direction, and west is in this direction. So if I have object on 115 degrees, so that means my face is facing east, because bearing of 115 degrees is second quadrant, so that means between 0 and 180. So if this is my face, so this is my face facing forward, so these are my eyes and everything, so that means this is from 0 to 180. If this is 0, that means this is north and this is south. So that is how I determine where the north and south is going to be. If the bearing was 200, and my face is like this, if my face is like this and I'm looking at the star, so that means north is here, and then it goes 0, behind my back 90, 180, 270, 360. So everything that I can see is between 270, is between 180 and 360 on this side. So this, what we are drawing here, is a 3D perspective of sphere, and we are focusing on the side that is actually visible to us. And what is visible to us, if we are observing a star that is on 115, is the section of horizon that is between 0 and 180. We still do not have the information where is east or west. We're going to get that later on. So that's the first step. You draw a horizon. The angle of horizon is not important. You just pick where you're going to stab and you draw a circle to get that 3D perspective. So when I said here 7.5, it's not a calculation. I just picked any number so I get the drawing going. So now that we have that, the next step would be to draw our latitude. Our latitude, because I could not draw this because I didn't have the information where is north, where is south. But now I know where is north. And I know that I'm 14 degrees away from the north. So that means is I need to draw a line that is 14 degrees away from north. So this is north, this is 0. And here 10, 11, 12, 13, 14. And I made a dot here. And then I connect this and I make intersection. Once again, this line on its own, it's not important. This is just a guideline for me. And this guideline is, where's my black? So this here is my latitude. If my latitude was 40 degrees, I would put it here. If it was 30, it would here. 60 would here. So that is how I determine this line here. Now, this position here, this is north on my horizon, and this is where north actually is on the sphere, and this is where the south actually is. Now, I don't have, where's the, give me a moment, I'm going to show you something. Let's see. Here. This is what I need. Here. Just Samsung. Okay, skip add, mute is on. Okay, let's put it inside. Okay, let's draw Greenwich. Okay, so this is one of my videos. You can, it's on Croatian language, but you can watch it. It's on my YouTube channel. So what I have here is, if you can see, yes, you can see it. So this is Earth, and this is that glass imaginary ball that we are imagining. And what I'm going to show you here is the reason why I started the video. This video is, so if I'm on Earth, location of my geographical north is here in this direction, is here, but the north on celestial sphere transferred is actually here. And the angle between, if you can visualize that, the angle between horizon north, so north of my horizon, direction of geological north or true north or Earth, and the angle between celestial north is actually my latitude, the angle of my latitude. Now this is this is just pure mathematics. This is how celestial sphere works. The angle between your horizon and the north on your horizon, and the difference between that same north transferred on celestial sphere. So this position here, copy paste on this glass ball surrounding the sphere, the angle between those two is your latitude. That's the whole concept of celestial sphere. That is the difference between true north and celestial north. Now to go back on my camera. So that is what we have here. We have the north on my horizon. That is direction of my north that is physically on Earth, and this is north, that same north copy paste on the surface of imaginary glass ball that is surrounding the Earth or celestial sphere. Now I believe we all know what is at 90 degrees from the poles. If this is north, what is 90 degrees away from the pole? So we plot a line, 90 degrees angle, and 90 degrees from north or south pole, we have the equator. We have the equator. And now, in order to draw the level of the equator, we cannot now change the values. We need to use the same value we used for horizon. So I actually took my position and point a dot here that is 7.5. So that means I need to use the same thing here. 7.5 from the center and 7.5 from the center. This is the location where I'm going to stab my divider. And then I connect, and this is full. This is full because this is the part of the globe I can see, and this is broken line. Come on. And because this is equator level, usually it is represented in color green. So this is visible side, and this is side behind my back. Good. And now something magical happened. We have intersection between our horizon and the equator here and here. And that means north something, south something, north. What is between north and south? East. And what is between south and north? West. So this is how you get point of east and west. It is the intersection between horizon and the equator level. So surface of the equator and surface of the horizon. Is this part clear so far? So this is our sphere for a person that is 14 degrees north. And it's observing an object on the sky between 0 and 180. So this is still not for this specific star. This sphere can be used for any object that is on 0 to 180 if we are 40 degrees north. So that is how we plot a sphere. We start a sphere if we are 14 degrees north. Another possible question would be, what if these two numbers were the same, but the latitude was 14 degrees south? So still this is my visible side. This would be my visible side of horizon. Still north would be here and south would be here. But if my position was 14 degrees north, I would actually plot the line like this. So because I'm 14 degrees on the south side. So this everything is the same. The only difference would be the equator level would be here, depending on the value of your latitude from the south side. Matthew, is this, if you are still here, Ivan, if you are still here, Red Dragon and everybody, is this clear so far? Just give me, blink twice if you have been held hostage. Let me take water break until you respond. Ah, where's my water? I lost my water. Oh. Good, Matthew. Is this clear so far? Okay. Maybe I skip a step explaining why we are doing this. 300 years ago, they didn't have fancy calculators, they didn't have GPS, they didn't have, didn't even have tables. You know, when I give you a book, like for example, if I give you, where is it? When I give you this book, and you roll your eyes, oh come on, let me show you how thick this is. Oh, you say, oh Marina, this is so old, this is history, this is like Stone Age. But this was actually an advancement, because before this, what they actually did is this. They didn't calculate anything, they just draw a picture. And they could get their position from the picture. So it was very important that you actually know how to draw as a seafarer. So this is basically in Wednesday or wherever we get to that point where we start calculating things on the calculator. All of that can be skipped if you know how to draw. Usually when we were in college, our teacher would give us, where is it? He would give us this. So micromillimeter paper with marks, and if you draw this on this paper precisely, you can get the result without any calculations. You can get your position from the drawing itself. So, but that's drawing. And let's continue. So, if this is clear so far, now we actually need to plot this star here. So this star has two coordinates. It has angle, that's azimuth, and has height, how far it is from the horizon. So that is what we need to plot now. So if this is north and this is east, that means from here to here, this is 90 degrees. If this is east and this is south, that means from here to here, it is 90 to 180. So that means this portion here, I need to split, because this is what I need. I need 115. I need to split this, and I'm going to use the pen for this, approximately on 8. Wait, so this is 90, 100, 110, 20, 30, 40, 50, 60, 70. So that's 8 parts. So I need to split this approximately on 8 identical parts. So 1, 2, 3, 4, 5, 6, 7, 8. Now this is what I told you. If this was done on millimeter paper, it would be more precise. This is just me guessing, but you can do this as well. So just visually split this on 8 or 9 parts with 8 lines. So this is 90, 100, 110, 20, 30, 40, 50, 60, 70, and 180 is the south. So now that I split this, let me use purple. I need 115. So this is 0. This is 0. This is 90 degrees. This is 100, and 115 is approximately here. So this is my azimuth true. So this is the angle. This here is azimuth true. This is the angle where I see the star. And now I take a divider and I need to connect zenith, this point here on the horizon, and nadir. So zenith, this point where the azimuth is, and nadir. Now the way to do this is basically you have to, okay, like me, guess from the first. So what you do is you stab around here. You can even go inside until you get the best angle. So what I did is I stabbed here and I get this. And this is my height circle. So height circle is circle where you measure height on. So between zenith, horizon, and up to nadir. So everything from here to zenith is what I can see from the horizon level to zenith. Now the same rule applies from the horizon to zenith is 90 degrees. So now I need to split this section on 9 identical parts. So I need 8 lines. So that would be 1, 2, 3, 4, 5, 6. Oh, it's smaller. 1, 2, 3, 4, 5, 6, 7, 8. So 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees. Once again, if I was using millimeter paper, this would be more precise. And I need to plot here 42. So that means 10, 20, 30, 40, 42 is approximately here. And this is the location of my star. So this here is the height of sextant from my position. So this is the location of the star. I have 42 degrees. That is the distance from the blue line on the line or circle that is connecting zenith and nadir. And I have 115. That is the angle on the blue line. So height is angle from the blue line, from the horizon, and azimuth is angle on the blue line, so exactly on the level of horizon. And now that I have position of the star, let me show you how that looks like. This is, let's hold the observer. So this is observer, and this is what he sees. Come on, observer, stand still. This is what he sees. And this is the level of his horizon, and this is the level of the equator, and this is the height. And from here all the way up to here is the bearing. And let me see, what is this? This is for an object that is 20 degrees. So if it's 20 degrees, that means this is north. So this is 20 degrees. So observer is here observing the star that is 20 degrees away from his north and 40 degrees away from his horizon. And this here is the next step that we need. So at this point we have the zenith and nadir, and we have the height, and we have the bearing. That is how far we are when it comes to celestial sphere. And now the next step is to do this. And let's do that. If I connect north, pole north, so the north that is on celestial sphere, and pole south in a such way that it's crossing the object, crossing the star that I'm looking. And once again, I need a divider. So I have this guideline for the equator, and what I have to do is stab somewhere here, and I need to find the star. So shorter, let's see, even shorter, closer. Okay, so it will be approximately here. This is a point of guessing. Okay, this is it. And let me just read this value for you so you know where I stabbed. So around between 3 and 4 centimeters from the center, that is where I stabbed in order to connect pole south object and pole north. As you've seen me move, so this is just, you need to pinpoint what angle is going to connect pole south, pole north, and the location of the star. I draw it here, but it's actually here, and I need orange. So I connect pole south, I connect star, and I connect pole north. And this circle here is called declination circle. So we have two circles. We have the pink one, this one, and it's called height circle. And this one is called declination circle. So on a height circle we measure height, and on declination circle we measure declination. And let's see Where is the, come on, skip ads. And now, I wish I could zoom this in. So basically I have this green line representing the equator, and obviously the star is little under the equator, so on the south side of the equator. This section here between the green line and pole south and green line and pole north is declination 0, 90, 0, 90. Now what I need to do is I need to split this on 9 identical parts, but I don't have to because the star is very close. So let's do it. 10, 20, 30, 40, 50, 60, 70, 80, 90. So it's little under 10. Little under 10. Let's say I'm going to call it. Once again, if this was drawn or millimeter paper, it would be much easier to actually read the exact value. But to me, this looks like 8 degrees. And because it's under, if the star was here, it would be over, but it's under, so on the south side of the hemisphere. So declination is 8 degrees south. So 8 degrees south. So that's the first thing I calculated, or I read. I didn't calculate, I read from the celestial sphere. The second information I need is I need local hour angle. I do not have Greenwich here. I do not have Greenwich. So basically the angle I measure here is going to be local. So that is our angle measured from my position, so my location. And I measured that on the equator from here, not from here, because this is an invisible part of the equator, so from here. And this is important. Azimuth is measured in a clockwise direction over the point of east. Local hour angle is measured in counterclockwise direction across the point of west. So it's not measured like this. It's measured like this in this direction. So I have 0, I have point of west, so this is 90 degrees, 180 degrees. This intersection is 270 degrees. And now I need to split this part here on, once again, 9 identical parts. So I have 1, 2, 3, 4, 5, 6, 7, 8. And now I need to measure. I don't have, this is why I told you need multiple colors. Do I have another shade? I don't have another shade. I have brown. I'm going to use brown. So all of this around up to the star, this is local hour angle. And the local hour angle is, let's measure it. Where's the black? So this is 0, 90, 180, 270, 270, 280, 290, 300, 310, 320 degrees approximately. Let's see. Where's my life? So 320 degrees approximately. And that is how you draw a celestial sphere. And now, once again, if this was drawn on a bigger paper, in the millimeter paper, with more precision, you can actually now use the sphere to calculate from here this or this from here. So if you know this, you can calculate this, and if you know this, you can calculate this. So these two values are joined together. Now, let's see how is a mariner calculating this or this in either direction without drawing the sphere. So let's see how off I am. Now this is advanced. This is what we're going to do tomorrow and the day after that. So just ignore me for a moment. So I have this cosine of 40 times cosine of 42 times cosine of 115, shift cosine, shift, no, it's sine, shift sine. Okay, so the answer I got mathematically, so if I do not do this, if I just use calculator, is minus 8 degrees 13 minutes. So from the picture I have 8, from the calculator I have exactly 8 degrees 13 minutes. So that means my drawing is off by 13 minutes. 300 years ago, that is nothing. That is more than enough to get accurate position on chart. Now that I have this, let's see how off I am with this angle. So the angle is this number, minus 8 times 14, 42, cosine of 14 times cosine of 42, shift cosine, minus 360, no, 90, maybe I made so minus 8, I put times, give me a moment, calculator, shift cosine, minus 360, 245, that's not supposed to happen. Yeah, it is 114. Yeah, that's the result. Yes, 100, and so the angle is supposed to be 115, but the mathematical is 114.7. So 114.7. So that means my drawing was off by 0.3 degrees. So 0.3 degrees is how my drawing is off. So the actual value is 114.7. That was what I would get mathematically, and the drawing is worth got me 115. So 0.3 degrees of error from this and this is basically nothing. But this is how you draw celestial sphere. You have height from the horizon, you have bearing on the horizon, you have how far the star is from the equator, and you have how far the star is from Greenwich meridian or your meridian. Celestial sphere, to understand celestial sphere, the best thing is just practice. You need to draw a couple of these in color. I always suggest to draw it in color to understand what you are doing, and follow the steps. So don't skip a step, don't skip a color. So imagine I did this in black and white. It would be completely strange to understand what is what line is what if we did it in black and white. But this is celestial sphere. Basically, what we drawn here is we drawn what we have on the sky, and now we can use this. We can measure all these values from here and get our position. What's missing here is another star, so I need to repeat all of this on the same image for another star. But that will just, for me, I would understand what I'm doing, but it will be just too much of the scramble here on one image for you. So right now, what I want you to know today is how to draw celestial sphere for just one star. That is the goal, and I hope the video or this live tutoring was clear enough for you to follow what we are doing here. So basically, this image drawn like this is drawn professionally like this. This is how you professionally draw a celestial sphere. 300 years ago, 200 years ago, they would actually continue with drawing to get their position. They would not use calculators, they didn't use tables, they would just continue with the sphere. But of course, today we have calculators, so we are using calculator. You do not need to know this for the exam if you are attending master's exam. So for the master's exam, you need to know this, but for the officer of the watch, you don't need to know how to calculate from this, but you need to know how to draw this at least once. And don't worry about the numbers if you get them wrong at the beginning. Like I said, it all depends how precise you are. So visually, can you split this on 9 identical parts easily? So that just depends on you and your skills of splitting. Can you, for example, if I ask you to split this line on 9 identical parts and this line on 9 identical parts, can you actually do that easily, or if that is a problem for you? How do you feel so far? Do you want me to continue? I mean, I told you at the beginning, this is a big problem for me. Celestial navigation, I can talk about this until next Christmas. If you want, I can continue. Maybe we can continue in the afternoon after a short break, or we can just move on to the next subject. Celestial sphere is finished. So the elements of the celestial sphere are observer, northeast, southwest on the horizon, zenith and nadir above and below the observer, celestial north and celestial south, line of the equator, declination circle and height circle. So those are the elements of celestial sphere. Take a pill, Ivan, take a pill. You are, you know how they say in the Lethal Weapon, you are too old for this. If you are 13, you are in high school and the teacher is giving you pencils to color something, this would be fun. This is 70 hours. This is one semester, entire semester in high school. We call this drawing balls in college. You just spend 6 months in school drawing balls. If everybody is more or less except the one who is sick, okay? I would like to move on to the next step. So what would be the next step? Next step would be, now, I have these two numbers, I have these two numbers. What do I do with these numbers? All of this is for my position, and this is my assumed position. I have no idea where I am. This is my assumed position. Now, I need to get the same thing. I need to get the same thing for my true position. And now we go to almanac. So the next, it's first hour of celestial navigation is finished, and what I would like to do still today to finish it off is I would like to go through nautical almanac and show you what you have inside of this. Okay, so I'm going to show you. So no matter where you open, you pick a page, it doesn't matter where, you have this. And I know technically you have this and this, but this is considered as one page. No matter what almanac you purchase, is it UK, Brown's, Admiralty, Croatian version, American version, no matter which one, they're always aligned like this. So when you open anywhere in the almanac, this is considered one page. This is the left side, this is the right side, and this is one page. On the left page you have data for planets and stars, and on the right page you have data for sun and moon. And in 100% of situation, everything is identical, 100%. So no matter what, even Russian almanac, it has some strange values that I do not understand. They are maybe using different poles or something, but every other almanac out there is identical when it comes to arranging of the elements in the almanac itself. So I'm going to go through these 2 pages to explain to you what actually you have here and where you're going to use it. So let's close this up. You have the link. This is Nautical Almanac specifically for education. My theory book that is going to be available next month, I hope. And also textbook is also going to be available next month, I hope. It's going to be as per this Nautical Almanac for education. So all the tasks, all the examples, everything that is going to be calculated in the textbook as example is going to be as per this Nautical Almanac for education. And you have a link in the description where you can get this one if you want to use it for practice. Also, this is what I'm going to do with you now. I'm going to explain to you all of these parts, and as you can see in the almanac, they are in color, so each element is in own color, so you can read what is the meaning of this, what is the meaning of this part in the almanac if you get the book. But let's go. Okay, so we have left page, right page. Okay, so left page, right page. Let's first focus on the left page. Every page has 3 dates. So this one is for July 23, 24, 25. So 1 day, 2nd day, 3rd day. Each day is split into hours, even hours, so from midnight to 23, and midnight belongs to another day. So midnight 23, midnight 23. And what values we have on this page here? So here in the first column, we have Aries, and we have Greenwich hour angle of Aries. So what is Aries? What is Aries? I'm going to just give me a moment. Let's stretch. This is sun, and this is everybody around. Now, everybody is spinning, and plus Earth is spinning around itself, so there's a whole bunch of spinning going around at any given time, at any given moment. Now, if we want to calculate something, what we need, let's say I ask you, okay, can you measure me 3 centimeters? You need to know where the 0 is in order to measure something. So the 0 of something is always very important when you are measuring anything. So you need to know what is the 0. So for example, for compass, north is 0. For, I don't know, for mathematics, the level ground is 0, and then 90 degrees is straight up. So the 0, knowing 0 and where 0 is and what 0 is more important than actually measuring something. That comes after you knowing where the 0 is. In this situation, sun is spinning, everybody's spinning, Earth is spinning, everything is moving. So what is 0? We need to have something here to be 0 in order so we can say, okay, this is 0 and this is where we're going to start measure things. Now, there is something interesting that happens 2 times in a year. So 2 times in 365 days. Let me get a paper. Where's my block? So something interesting happens. This is sun. And this is Earth. Spinning around the sun. And this line here that I draw, this is the axis of Earth rotation. So when the Earth is spinning around the sun, it's not doing like this. It's not going like this. It's not spinning like this around the sun. It's actually spinning at an angle. And that angle changes position. Actually, this change of position of the axis is called precession. That's the name. So it's changing the angle. So it goes from here to here and then here. So basically, if I have Earth tilted, this is summer, winter. So summer, winter, summer, winter, summer, winter. And here we have autumn and spring. So autumn and spring is where the sun is exactly on the equator. So that is where the axis is like this. So when we are calculating something and we want to make it simple, the simplest way is to have either multiplication with 0 or multiplication with number 1. So which one is easier, to multiply something with 0 or multiply something with 1? What do you think? So the easiest way to simplify mathematical equation is to have everything multiplied with 0 or everything multiplied with 1. My question is, which one is easier, to have everything being multiplied with 0 or everything that is already in the equation multiplied by 1? There is a lot of delay, but I hope by the time you start typing the number is going to be 0. So why do we pick 0? Yes, Ivan, the reason why we pick 0 is because no matter what's in the equation, the answer is going to be 0. If we multiply it with 1, we're still going to have to calculate the entire equation. So we pick 0. Now, declination, if you remember, declination is the angle between an object on the sky and the equator. If the sun is exactly in the level of the equator, that means his declination is 0. So you have something around 23 degrees, 0, something, 0, something, 0. So we have two options where we can pick sun to be our 0, to be our key element for calculation. We have moment of spring and moment of autumn. The problem with autumn is you have clouds and you have rain and you cannot see the sun. So that's why we pick this moment. We pick this specific moment. Where is the earth? Get away. We pick this specific moment in time where sun is going to be exactly on the equator, meaning his declination is going to be 0. And we picked spring because in autumn we cannot see it because of the clouds and rain. So this position of the sun, photo, picture. So we have earth and sun frozen in this position, and then we just let go everybody to continue to do their thing. Earth continues to move, but we are still measuring as earth was here, as sun is here from position of spring. And that is Aries. Aries is the term we use for point of spring. That is frozen image in time where sun is at the first moment of spring. So that is where the sun is exactly at the level of the equator. So exactly here on the level of the equator. And that is the reason why we selected that position. That is the reason why we didn't select any other position, is because it makes calculations easier, because the declination at that moment for the sun is 0. Declination is distance from the equator, and if it's 0, as you can see here, we do not have declination for Aries. Declination of Aries is 0. The only information we have for the spring point is how far it is from our Greenwich meridian. So Greenwich hour angle. For another 4 planets, Venus, Mars, Jupiter, and Jupiter, and Saturn, we have Greenwich hour angle and declination in degrees and minutes given to us. So this can be calculated in advance, and this doesn't depend on us. So no matter where you are, this is where Venus is going to be at this date, this hour. This is how far it's going to be from Greenwich, and this is how far it's going to be from the equator. I see Matthew said 1, but I hope now it's clear why it's not 1, it's actually 0. So that is why we pick Earth position where the sun is exactly on the equator, because declination is 0. And when you have that formula like sine of declination times sine of bearing, sines of this, sines of this, sines of 0, sine of 0 is 0, and sine of 90 degrees is 1. So that is why we pick 0, because it makes our calculation easy, because it cancels out most of the parts in the equation. So on the left page we have Aries, so that's a spring point. That is how far the image of the sun frozen in the first moment of spring is going to be in entire year. So it's basically a circle that goes from 0 to 360. So every day it's 0 to 360 for the spring point. For Venus also, and Mars and Jupiter and Saturn. Declination is how far it is from the equator, and Greenwich hour angle is how far it is from Greenwich. So basically, if we go back here, if this is the equator and this is Greenwich, and I say, let's say I pick Jupiter on 23, 4 o'clock, 74 degrees, so I would measure here 74 degrees, and 22 degrees south. So this is location of Jupiter on 23 of July in 4 o'clock in the morning. And now, depending where I am and can I see it, I can use Jupiter, and if it's nighttime, of course, I can use it to get my position. Now, on this section here, we have list of 50 or 55 navigational stars. These are one of the brightest stars that you can actually see on the sky. Some of them are always visible. Some of them are visible only for north hemisphere, and some of them are only visible for south hemisphere. You do not need to know everything. You do not need to know all of them. Usually for practical celestial navigation, I advise that you pick 10 of them, 5 for one sphere and 5 for one hemisphere, so north and south hemisphere. Whatever you see during summer on north, you can see on winter during on south during the winter. So if you pick 10, 5 from north and 5 from south, throughout the year you will be able to see most of them. You need minimum 2 for pinpointing your position, so you just need to pick 10 out of these and memorize how to identify them. So when you look at the sky, you know, aha, that is Orion, and that is Betelgeuse, that is Bellatrix, that is Deneb, that is the Nebula, that is Menkar. They are quite, I mean, if you ever looked at the sky, you probably noticed, I know everybody spots the bears, but that's not my favorite. The one I prefer is Orion. So you have one here, one here, one here, one here, one here, one here, and one here. So this is the Orion belt. So you have 3 stars like this, 3 stars like this, one smaller here, and one huge one here. This is Sirius. This is the brightest star that we can see. It is, I don't know, I'm just guessing, around 10 billion times larger than our sun. So it's one of the largest stars that we can see at the moment. And it is the brightest star on our sky, Sirius. And this belt here is Orion, and this is Bellatrix and Betelgeuse. And Rigel is here. So usually I pick Sirius and one of the stars from this constellation when I'm using it for my positioning. So you will not use all the stars, you just pick a couple of them that you can easily visually identify, and then you use them for navigation. And you come here and you have 4 stars. As you can see, you have 1 day, 2nd day, 3rd day on one page. But for stars, you only have 1 column. The reason why you have 1 column is that the position of the star doesn't change by that much in period of 3 days. Actually, for some stars, it doesn't change in period of 6 months or even during the year. So if you are observing this star on 23, 24, 25 for all 3 days, any moment, you are using the same value here. So it doesn't matter. It's different for planets. Planets are close to us. All of these stars are far away from us. So that's why for planets we have specific values. But for stars we have these values that are the same for every moment during the 3 days. Now, something to note. For planets, we have Greenwich hour angle. For stars, we do not have Greenwich hour angle. We have SHA, that is sidereal hour angle, and declination. Declination is how far it is from the equator. But what is SHA? What is that? Now, we have Greenwich meridian, and we have a star here. And we have John here in Italy. That's 14 degrees east from Greenwich. Now, from Greenwich to star is Greenwich hour angle. This is what we need, but we do not have this. We have SHA. Now, what is SHA? Star is visible, but it's very far from us, very far, and the Earth is just tiny little this dot. So to measure from here to here, it's very hard, but we have advantage, advantage. We have this big star that can match this star because they are both stars. They can be seen. And let me pick a color, just put green one. This is not just any sun. This is sun frozen in the position of spring. So that means this is Greenwich hour angle of Aries. So not sun that is moving up, not approximately, how to say, the sun is not moving, we are moving, we are spinning around it, but that illusion of movement of the sun is not this one. This is sun that is frozen in the position of spring, and then we are moving around that position, imaginary position of frozen sun in the spring point. Sidereal hour angle is angle that can be measured because you see this tiny dot, this is Earth. And this is a big bright star closest to our planet, Sun. And then we have big bright star somewhere in space. The angle between two stars is called sidereal hour angle of that unique star. Now, we need the black one, and we have green and purple one. How do we get black one? This plus this. Simple. So here, the first column is this green value. This position depends on the time and date. So that is this value here. This value is more or less the same throughout the 3 days, and it is for each unique star individual value. So Greenwich hour angle of Aries plus sidereal hour angle of star gives me Greenwich hour angle of the star. So what does that mean for John? For John, that means if John is here, from his meridian all the way up to the star, this is local hour angle of the star. If John is east, then I need to add, because remember east is plus, so this plus this gives me local hour angle. If John was west from Greenwich, it would be this minus this, because west would be negative, and I would get this as a local hour angle. And what is the relevance of this number here? The relevance of this number here is, ta-da, this one, local hour angle. So by using this, so I got this. John is on Earth. He doesn't know where he is. I get this number. And from the almanac, I get this number. This number subtracted with this number gives me his longitude. And I get this from here. And this I get from almanac. This minus this gives me longitude. That's the core of celestial navigation. And now you can also see why it is important to know the sign. Why I cannot just put 14 degrees. I need to know, is it east or west? If I get the value negative, it's west. If I get value positive, it's east. So the signs are very important. I cannot just put everything positive, everything negative and hope to get accurate result. I need to put exact sign in front of each number in order to get result. So that was first page, this page. Once we start calculating, once we start using this page, it's going to be easier for you to follow the numbers. But right now, I just need you to understand what we have here. We have Greenwich hour angle, we have declination. Greenwich is how far any object that is listed here is from the Greenwich. Declination is how far it is from the equator. For the stars, we cannot have that directly for the stars because they are too big and too far away from us. So that's why we need to cheat. We need to use our star, biggest, closest star, sun. But in order to simplify the calculation, we do not use sun that is actually moving around or we are moving around. We actually froze the moment. We pick one moment in 365 days to be our zero, and that zero is spring, where the sun is exactly on the level of our equator and makes the calculation easier. Everything else except Greenwich hour angle becomes zero. So this is Greenwich hour angle of Aries. Aries is the term used for spring point. Sidereal hour angle doesn't depend on us. It's distance from the sun towards any other star. These two together are Greenwich hour angle. This number is obtained from here by drawing or mathematically on calculator. And this number subtracted by this number gives me my longitude. And that is how I get my longitude. The next part that we're going to do tomorrow is how to get latitude. So this is in this direction. All the time we are moving in this direction. So this is how you get longitude. Latitude is in this direction and latitude is separate procedure. So this is left page of the almanac. Right page of the almanac has sun and moon and lots of extra data for the sun and moon. So for the sun and moon, we have Greenwich hour angle. This is not Aries. Remember, the Aries is frozen sun in the position of spring. This is the actual sun approximately moving around the earth. And declination, how far it is from the equator. For the moon, we have the same values. Greenwich hour angle, declination, plus moon is very close to us, and because of that it has a specific unique corrections V and D. Once we start calculating with the moon and with the sun, I'm going to explain to you what V and D are actually is. Also, moon has horizontal parallax that is very unique for the moon as well, so only moon. So people say moon is too hard, and usually in no exam anywhere you have moon as observed celestial object. But moon is not complicated per se, What is the trick with moon is that instead of having one unique correction like sun has only one unique correction, moon has an individual correction for each hour. So still sun has a correction, but it's only one correction. Greenwich moon has individual correction for each hour. So it's still one correction, but it's different for every hour. So that's this part. This part here is if you want to observe sun or moon, but mostly sun, during sunrise and sunset. So here in this section you have latitudes between 72 degrees north and 60 degrees south. So you enter this table with latitude, and you have nautical, civil, and actual sunrise. And we are using this one. So sunrise, and on the bottom, sunset column. So let's say for observer that is 30 degrees north on July 23, or 24 or 25, doesn't matter. The sunrise is going to happen around 5 o'clock and 14 minutes. So 5 hours and 14 minutes. So that is how you use this section here. You have your latitude and you have the time of sunrise. Why would you need that? If you want to check your compass, is there an error in your compass, you would come to almanac for your approximate position. You would check the moment of sunrise in advance. So this is not something that you do after you measured. You do this in advance, so you can go outside and actually at that time of sunrise you can actually measure exactly at moment of sunrise the bearing of the sun, and by using the values that you get from this page you calculate the bearing that's supposed to be for that latitude, and that is true bearing. So difference between the true bearing and what you measured on your compass is going to be the error of your compass, minus variation of course from the chart. So this is sunrise, this is sunset, and this section is also very important. So bottom right of the sun and moon page, this is where you have true noon information. Now if I have solar clock, you see the shadow here falling down, and I have a human clock here, they're not going to show noon at the same time. There is small error between what the actual noon is and what me or you or everybody as human measure as true noon. And that error is called equation of time, and it can shift between, where's almanac? So let's see the bottom here. So you have 7 minutes, 8 minutes, 6, 3, 1, 2, 10, 12, 13, 14, 15 minutes. So it can go 15 minutes plus minus during the year. So what that means is equation of time is minutes and seconds between the true noon and human noon, where the sun is in your meridian from the time that your clock is showing as the position of the sun in meridian. When the sun is in your meridian, that is the actual astronomical noon. So here on July, the error between the real noon and the human noon is 6 minutes and 30 seconds. So 6 minutes and 30 seconds. And it's plus, so that means when my human clock is showing 12 minutes and 12 hours and 6 minutes, it will going to be actual noon. So at 12 o'clock and 6 minutes, that is the moment of actual noon. And that is the data that we get here. And that is called meridian passage. So this is the moment in time, this one, this is all for Greenwich. So this is the time when the sun is going to be directly above Greenwich meridian. So it's going to be around 12:06. 12:06. So that is the actual noon happening around 12:06. So to go back, left page, right page, Aries, 4 planets, all the stars, sun and moon on the other side. In most cases, people make mistake between Venus and sun because they are approximately on the same location. So when you are using almanac, first make sure that you are on the correct page, make sure that you are looking at the correct date, and make sure that you are looking at the correct section. Last group, they all, the task was Sun, and they all used number for Venus. So read the name on the top of the column. If the task says Sun, use the Sun on the top. If the task says Star, use Aries and Star section. Also, each day has 24 hours. Make sure that you pick correct date. So 23 is here, 24 is here, 25 is here, and then 24, 7 o'clock is here. Use ruler or triangle to find the numbers and then write them down in your textbook or notebook. Okay, what else? Okay, let's switch to the exam. I will go back to exam. PDF. So that was this section. So the next part, the question number 3 on the exam, preliminary exam, is what is declination? So declination is the angle between the equator and celestial object. So that's declination. What is spring point Aries? Spring point Aries is position of the sun when it's exactly on the celestial equator. So when its declination is 0, that's a spring point. What are circumpolar celestial bodies? Circumpolar celestial bodies are celestial objects that do not have setting or rising. So that means they're always above the horizon. So for example, Polaris, pole star, is a circumpolar celestial star. So she doesn't have a setting or rising. So she never crosses the horizon. She's always above the horizon for a person that is on north hemisphere. What is a great circle? Let me draw you that. So great circle is, so we have Earth and we have center of the Earth. Any circle that you make that goes through the center of the Earth is great circle. The biggest great circle that you can make is the circle that is splitting Earth on two identical halves, because Earth is squashed a little bit on poles. So that is the equator. Equator is the great circle. So all of this are great circles. This is not. These are small circles. So if the circle is connecting 2 points on Earth, but it's not crossing the center of the Earth, that's small circle. Big circles are circles that are crossing the level of the center of the Earth. So let's say I have this position and this position. If I connect them like this is a small circle. But if I connect them like this, so it intersects the center of the Earth, that's a great circle. And great circle is the path, the shortest path between two positions on the Earth. Let's go back to the exam. The next question is, name the celestial coordinate systems. Celestial coordinate systems are, let's go back to the image. Camera. Okay. So we have 5 of them, but we are only using 4. We are only using 4 in celestial navigation. So first one is horizon celestial coordinate system. Horizon means that we are using coordinate system. The name says it. You have 2 coordinates. Horizon coordinate system is using height, that is how far you are from the horizon, and bearing, that is your azimuth on the horizon. So if I want to say the location of this star and I'm using horizon coordinate system, I would use bearing, azimuth, and height. So that is how I determine the position of an object in horizon coordinate system, azimuth and height. The second coordinate system is called celestial equator system. Celestial equator system is using hour angle and declination. That is how you pinpoint object on equator coordinate system. So hour angle and declination. Hour angle and declination. And you have local equator coordinate system. The difference between that one and the first one is this one is using hour angle and the second one is using local hour angle. So local hour angle. So you have local hour angle and declination as coordinates. Number 4 is galactical, and galactical we do not use. So you only need to know the first 3 ones that are the most important one: horizon coordinate system, equator coordinate system, and local equator coordinate system. Okay. And that is, if you look at the exam, that is the next question after you name the celestial coordinate system. Name the main coordinates of each celestial coordinate system. So like I said, for horizon, what do you measure on horizon? You measure bearing, you measure azimuth, and you measure height. For the equator, you measure hour angle and declination. So for the equator coordinate system, what do you measure on the equator and from the equator? You measure on the equator hour angle and you measure declination from the equator. If it's local equatorial coordinate system, then it's local hour angle. So it's not just hour angle, it's local hour angle. What's next? Now, question number 7, content of almanac. So, as I showed you here, content of nautical almanac is you have Greenwich hour angle for every object in the sky. You have Greenwich hour angle of sun, planets, moon, and for the stars you have sidereal hour angle. For everybody you have declination, how far they are from the equator, and also you have time of sunset and sunrise, and you have the moment of true noon or meridian passage. So that's the content of almanac, main pages. Question number 8. How do you find, and Ivane, ovo je ispit na poročničkom, na usmenom. So this is one of the exam questions on oral exam for masters and officers in Croatia. How do you find exact moment of beginning of spring and autumn in almanac? So let's just do that and we will finish for today. So how do we find the exact moment of spring and autumn in almanac? So basically what will happen is the captain is going to give you almanac. It doesn't matter which one, what year. And how do you find exact moment is you find if it's spring, you are looking for March. And then you look at the numbers here, 000, 000. And there is a certain moment on the page where it's going to cross from south to north. So it's going to be 0 south and it's going to switch to 0 north. So for the year when this almanac was developed, it happened on 20th of March between 5 in the morning and 6 in the morning. That is when the sun was exactly on the equator. First moment of spring is where the sun's declination is 0. So basically, the way you find it in almanac is you look for declination to be exactly 0. If it's spring, it's going to go from south to north and cross the equator. And if it's autumn, it's going to be, where is it? Here. So in September, once again you are looking north 0, turning into south 0, so it's moving from north to south in autumn. And for this almanac, that happened on 22 of September between 3 o'clock in the afternoon and 4 o'clock in the afternoon. And that is where the declination of the sun was once again 0. Sun is exactly on the equator because declination is 0. And that is how you point the exact moment. So this is the day of autumn, and this is the exact moment of autumn for this year. And it's been 2 hours. Let's see what other questions. What star is closest to Earth? So star closest to Earth is Sun. Don't forget that. Sun is the closest star to Earth. And another exam question is, how long is 1 day, 1 month, and 1 year on Earth? So let's view that. Let's go back to this. So we have Earth that is spinning around its axis. So one rotation of Earth around its axis is 1 day. So 1 day is how long it takes Earth to make one full rotation around its axis, so 360 degrees. So that's 1 day. 1 month is how long it takes for the moon to make one full rotation around the Earth. So that is 1 month. 1 year is how long it takes Earth to make one full rotation around the sun. So 1 day, 1 month, and 1 year. Okay. So that was for today. I hope you learned something. For people that are from Croatia, everything that I'm saying here, you already have this in my videos on Croatian language on my web page under Celestial Navigation. So under Astronomska navigacija, you have this here. You see Greenwich hour angle, what is declination, you have this planets and everything, you have all of this explained, so you can watch those videos. And for John and Matthew, tomorrow morning at 10 o'clock I will do another lecture. If you are here, great. If you cannot be here, that's okay. I will make the recording. The video will be here available on my channel for you to view whenever you want to view it. And tomorrow I continue with mathematical tasks that will be in the exam. So tomorrow we're going to start with mathematic calculations of each exam question that is going to be on the exam. And for Croatian students listening, all the questions that I'm going to go through are identical as you're going to have on your officer and master's exam. The only difference is going to be well, there's not going to be any difference because the almanac I'm using, the almanac that you just saw, this one, let me just bring it up here. Where's the mouse? Let me just click the link. Where's the basket? Here. So this almanac that I'm using here, this one, the almanac that I showed you, the almanac that I'm using for the STCV Yachtmaster courses for the exam, and that the government of Republic of Croatia is using in Harbor Office for the exam is identical. So it's the same almanac that they are using for the exam. So all the numbers that we're going to get while calculating them for the task are actual numbers that in case if you get the same task with same numbers, you're going to get the same results. Okay. So that is for tomorrow. We're going to use this almanac and we're going to do the calculations. Now what we did today is we actually make a graphic solution of the problem, and graphic solution is by drawing the celestial sphere. So when you draw a celestial sphere and you get the result, you get your position. You can do that like that by drawing, or you have mathematical procedure where you use calculator and or tables. So you have two options when it comes to mathematical solution. You can use either tables if you have them, or calculator if you do not have tables. When I say tables, I mean these tables. I don't mean almanac. You always need almanac. The tables I'm talking about are, where are they? This one. So you always need almanac. So almanac is the book that you always need. The book that you do not need if you have calculator is this one. Because basically what you have here is you have the results of everything that this can give you. So if I type in, let's say, sine of, that's a trigonometry function, sine of 42 degrees, and I get a number. If I don't have calculator, I would go here and I would look for sine. So tangents here, sine of 42 degrees, and you see it's 0.66913, and I have 0.66913. So in case I do not have calculator, I would use this book here. But when I say tables can be replaced by calculator, I mean these tables can be replaced with calculator. You still, regardless of this, you need this book, because this tells you where the objects are going to be at the moment of the day and hour and time where you are observing them. So these are not the tables I'm saying that you do not need if you have calculator. I'm talking about these tables. These tables give you all the numbers that calculator. So 9 times 6 is 54. You have that here. So if you don't have calculator, you have here multiplication tables and everything. So these are computation tables. So everything that calculator can give you, the results, you have that here. So if you know how to use calculator, use calculator. If you don't know how to use calculator, you can use this for the advanced calculations. But still, after you get these two numbers, you need to be able to add them or subtract them. So if you don't know addition or subtraction, then once again, you still need to use calculator. So tomorrow, 10 o'clock, we will start with the calculations. And the calculations is not going to be just pure calculation, because I already have that on my channel. And I believe my PDF, I'm going to show you. So for example, for the two known star, I have everything explained here, word by word. Where is this obtained? How did you get this number? So when it comes to calculations, I'm not just going to do the calculations, I'm going to explain each of these steps once. So I'm going to explain you once, and then I'm going to give you this document and lots of them so you can practice. So that's the plan for tomorrow. We're going to go through one task or couple of tasks of calculation with me explaining each of these marked numbers and values, how they were obtained. And then once we go through one and everything is clear, I'm going to give you a couple of examples so you can practice on your own. But in order to practice, you need the almanac. You need almanac. You can also use, I will give you the link, you can also use almanac that is available on internet. But maybe some numbers are not going to be identical, so just be careful about that. This calculation is done by using the Almanac for Education that I have published. Okay. And also, that means that exactly the same almanac is used on Harbor Office exam. So it's the same almanac. It has different front page, but it's the same almanac, same values for the exam. Okay. Okay. If you have any questions, ask me. I can continue. I don't have to stop after 2 hours. I know I said 2 hours, but I can continue. I have a couple of tasks I have to do, but I'm freelancer, so I can do them whenever I want. So if you want me to continue, if you want me to explain something to you, I'm talking about celestial navigation at the moment, you can ask me and I will continue to stream live. But if you do not have any questions, if everything is so more or less clear, I will stop and we will see each other again or hear each other again tomorrow morning at 10. Let's put the book back and planets back. Oh, so now it's awesome. At the beginning it was making you sick, or it's still making you sick, Ivan. Now, celestial navigation, I mean, the problem is they skip the fun part. They skip the fun part of celestial navigation and they just go directly to calculations. And we all know that there is a huge problem when it comes to mathematics and how education system is treating mathematics. You know that mathematics is not something that you have a plus A score. You only have either negative or positive. There's no 3, 4, or 5 when it comes to mathematics. And that's the problem. And celestial navigation, if you don't know how to draw, then it's all down to mathematics, unfortunately. Okay. We shall see each other tomorrow and we will continue with the lecture. I have to make order of all these papers I just spread all around my office, and let me just go back. This is the form that we're going to fill in tomorrow. This is the form for calculation. The letters in the bracket are for some people in Croatia, not everybody, but for some people in Croatia. And the now letters that you see on this side is what everybody is doing on the using on the planet. So Chinese are using this, everybody's using this, and in the bracket is just a couple of people in Croatia that are using these. But I put both so you can pick. And this is what we're going to use tomorrow, and I'm going to show you each of these individually, where it was obtained, why is it written like that, why there's a separation between each of them, and we're going to get the end of the result of this, and that is our actual latitude and longitude. That is the goal of the calculation, and this is what we're going to do tomorrow, step by step, and I think it should be very nice. Okay, thank you very much for participating. Thank you very much for communicating with me, so I know I'm just not talking to myself as I always do when I'm making the video. That's one of the hardest part, when you are making the video, actually talking to a microphone. But this is much more comfortable when I know that somebody's actually listening, so I know how to do it more entertaining and everything. Okay, I will finish. It's 12 o'clock. Have a nice day. See you tomorrow. Tomorrow we start with calculations, and relax. Have a nice day and goodbye. See you tomorrow.